I think this is afternoon, so good afternoon, everybody. I will try to speak slowly so the translator will not have a problem with me, because I noticed that he has problems with these faster speakers. I am going to talk about connections and Islamic art architecture in a wider context. Why I'm going to talk about something like this? You see, a few months ago I was invited with a lecture to Berlin, to Technical University, and the lecture was about geometry and architecture. And I was talking mostly about Islamic architecture, and at the end of the lecture, one of the professors said to me, "Why are you talking about Islamic things? We are from different culture. You should talk about Greek culture, Greek architecture, and connections there." So I asked him, "Listen, what is your specialty?" And he said to me, "I am the best German specialist in algebra." And I told him, "Listen, without Islamic mathematics, you would not have algebra, because they invented formula, they invented algebra." He was shocked, he was a bit mad on me, he left. But examples like this you can find a lot. For example, there was a time when I was visiting Sheikh Zayed Mosque in Abu Dhabi, and with me there was teacher of mathematics from Poland. She visited us in Abu Dhabi, and we went to the Sheikh Zayed Mosque. In the Sheikh Zayed Mosque, there are beautiful mosaics, there are beautiful patterns, everything is floral and so on. In one place, we saw very nice pentagonal pattern built out of flowers. And she said to me, "Oh, listen, that's imagination. Somebody had really good artistic imagination." And I said to her, "Listen, that's mathematics. That's geometry." And she looked at me and she said, "I don't believe it. I don't believe it. I don't see geometry here." She was a mathematician. She was a teacher of mathematics. So the point is that we often tend to look at things from our narrow point of view, and we rarely see things in a wider point of view. What kind of point of views we can have? First of all, we can have historical connections, a lot of historical influences all over the time. If you look at this sketch here, you see the Sumerian culture, then is the Persian culture, then is the Egyptian culture. These are just building all over the time. And of course, Persians took something from Sumerian culture, they developed this further, and that we have this way a Persian art. Then Egyptians, they also had some influence from Persia, from other civilizations. So everything what you find in Egypt is in some way based on other cultures. The same is in Greece. You see, the Greece, it is a very specific case. They developed very beautiful geometry. Geometry was really a culmination in Greece. But really what they did, they were traveling all over the world. They were traveling to Egypt, they were traveling to Persia, they were gathering ideas and then developed something on the base of this. The same is with Romans. Romans took from Greece a lot and they built their culture on this thing. And then what we have here, we have Islamic culture that is just taking from different sources, from Persian sources, from Egyptian sources, also the Greek sources, which are really Byzantine sources. And the Islamic civilization is building their art, their science, not only art, but everything, the science, based on this what was done in the past, and it was what was done in other cultures. And then we have the West. What we did really, we started working on this what we got from Islamic civilization. If you look at this, what we really know, we know small bits and pieces from the past. And we tend to believe in things that are completely fake. For example, we believe the Pythagoras Theorem was invented by Pythagoras. No, that's lie. That's really a lie. It has a name of Pythagoras, but unfortunately, the Pythagoras Theorem, not in the form of theorem, was used in Persia 2000 years before. It was used in Egypt long time ago. In Egypt, they were using a Pythagoras type of algorithm to calculate areas. Okay, so Pythagoras theorem was not invented by Pythagoras. His input into this was that he just created a theorem. He put this in a kind of nice words. He didn't put the formula because Greeks did not have formula. Formula were invented in Islamic period, not in the Greek period. If you take Euclid's elements, you will not see a single formula there. Then we tend that Thales invented the Thales theorem. That's not true. He brought the Thales theorem from Egypt. He was using this, he was learning. He was the student there. Come on. Then we suspect that Fibonacci didn't invent Fibonacci numbers. Okay? We tend to say Parthenon has golden ratio proportions. That's not true. Okay? There are many lies like this, many half-truths like this, because we just heard something and we repeat something, okay? We are not critical in our way of thinking about the world. We have really, in reality, very few manuscripts from the past, very few documents that we can trust. And we have architecture that we can look at it and we can build our conclusions. But these are only conclusions. When we are looking at the architecture, we can think, okay, this was created at this period, so there are these influences and so on, okay? But we don't have proofs for this. So what I wrote here, this is summary of what I said before. Ancient Greeks traveled to Egypt and Persia, and they learned mathematics, they learned science, they learned also art from there. They brought it in Greece. Then Greek science was translated into Persian and Arabic into 9th and 13th century. It was taken during the Dark Ages in Europe. Just look at this. This is the time. And then at the end of in the middle of 14th century, the Arabic documents were translated to European languages, and it happened in many ways, but it happened, okay, in majority cases in Spain, when Spain was conquered from the Arab civilization. So we have the movements. We have a chain of moving the knowledge from the past to our times. The key point for us is the House of Wisdom. House of Wisdom, it was the key point for Islamic architecture, for Islamic art, and Islamic science. This was the place which originated a lot of important things that we see here in Istanbul and in many other mosques. This is the place. This started here. And just remember, modern mathematics. The modern mathematics has its sources not only in Greece, but mainly here. The whole algebra, if you know the word, it was from this place. Before House of Wisdom, there was no algebra. It was Greek geometry, but there was no algebra. There was no formula. They didn't use formula before. So starting from this point, geometry became almost a sacred science for architects and artists. you have so many examples showing how geometry influences design. My colleagues were talking about art. I will just talk a bit about architecture because this is what is quite important. In the last line of this page, you see Abu al-Wafa Buzjani. He wrote a very famous book, and I will go back to this book just in a moment ago. So let's start looking at Islamic art. You know this place. This is the Dome of the Rock, very famous place, one of the oldest monuments in Islamic architecture. People say it was influenced by the Byzantine chapel of St. Mary. That is true. I believe that this is true, because when you look at the plan of the mosque and plan of the chapel, they are almost the same. So if you look at this, what they did, how they created this shape, it's an octagonal shape, but it is more than octagon. All these columns, all these pillars are put in the corners of the next octagon. How this octagon was created? By taking two squares and intersecting them. Then you have also internal columns over the stone, and they are also located on the intersections of lines. This is a very typical way how the Islamic architects, and not only Islamic architects, but also architects from the Byzantine time were designing their temples and the mosques. Okay? Here you have another example. The Samanids Mausoleum in Bukhara is quite early period. It looks like a cube. Okay? It is very nice design, very proportional, but it is built on geometry from the base to the top. This is the plan. You see the drawing, how it was planned already. By the way, if you look at this triangle, you have here a golden ratio. Okay? The golden ratio from the Greek time, it is going through the Islamic architecture, and you can find it in many places. So this is the Samanids Mausoleum. The floor, the facade, and here it is the section of the building. You see the proportions. If you take this point, you're getting just a perfect square, and this circle is determining a location of this level. Then you have another thing, and so on. This shape was created by using two circles. One is here. This is the center. Okay, this is the center of the circle. This is its radius, and this is the line. They used geometry all over. Then is another example, very similar but much more complicated. Sultan Sanjaya Mausoleum in Turkmenistan. It is using geometry all over. That's geometry. If you have this building, you look. This part, it is just the base. This is quarter of the base. Now, this picture here shows the quarter of this level. Then this square here shows the corner here. You see here we start getting octagon. Okay? And finally, this square here shows the cupola. And in the middle, we have the pattern on the ceiling. The pattern on the ceiling is built, if you see correctly, on two squares. That's one square, and that is another square. Okay? So this looks like this. Geometry all over. Bibi Khani Mosque, again, something that is quite important. You see, this is the shape of the ceiling. It is not a pure accident how the shape was created. It was created with geometry. What they did, they started with the segment A, B. Then, what they did, they put a circle like this. Then took the point C. What is the point C? The point C, the distance from A to C is half of the distance from A to B. So this part is half of AB. Then what they did, they put a circle starting from C and with the radius to A. They got this point. You remember, this is again golden ratio. This is what we have in Greek culture, golden ratio. And then they took another point, another circle from here to E. They got these two circles. So we have two circles like this. The one here, the big one, and the small one. And then they draw sections from B just across the circles. They get 2 points of intersection. For example, here is one, here is another one. They build two perpendiculars, and this point is based on the ceiling. So if you put many radii like this, you get perfectly the shape of the ceiling. Mathematicians at the moment, they will tell you, oh, that's ellipsoid. But they invented this thing. They invented the way of drawing precisely conic curves, ellipsoid. Ellipsoid was used all over in Islamic world for creating ceilings, for creating window arc. This was Islamic invention. Okay, I am talking too much about architecture. I have to go back to the point. Architectural design, this is what we are here. It means Islamic art. All this thing is geometry. This is Kyrgyzstan. Where is Erika? Erika is from Kyrgyzstan, and this is the example for Kyrgyzstan. Quite complicated designs, very geometric designs. Islamic artists were fascinated with 5, with the pentagon. So they used a number of proportions that are specific for pentagons. So, for example, here, if you take a segment of the length of 1, if you divide this angle into 5 equal parts, 1, 2, 3, 4, 5, if you draw the line, okay, up to the moment when it intersects with this, you're getting a square. This is one of the popular proportions. This one is another proportion derived from pentagon. Here's another way of designing ornaments based on pentagonal proportions. They were fascinated, and especially in the Central Asia, you can find many designs based on pentagonal proportions. But they used also techniques that are forgotten completely at the moment. For example, here what I am showing you a pattern that was based using Gnosis construction. You can find this construction in the book of those geometric constructions which are necessary for a craftsman. The author of this book is Abu Wafa al-Buzjani. This is a very rare book. You can find this book in Persian, a modern translation, and you can find this in one of the museums in Paris. I think probably there is one copy more somewhere else, okay? And in this book, there is a description of the Gnosis construction. The Gnosis construction is based on moving line in order to get here, for example, construct such a point on the circle that this distance from B to G is the same like the distance from E to G, okay? It is not a simple thing. Then based on this thing, okay, you see this is the point here, okay? And based on this thing, you're just building a pattern like this. Very beautiful pattern, and you cannot create this pattern using traditional methods. Only the Gnosis construction is giving you this pattern. And now in Abu Wafa al-Buzjani, you can find two more interesting. There's about 100 geometric constructions there. And here is one. Just try to remember the shape. It is using squares and it is using rhombi. And then there is another one which is using seven gun stars, which is quite a rare case in Islamic art. Seven-gun is a difficult case. Okay? Now, we are coming to modern times. You see, for centuries, mathematicians were struggling with some problems. First of all, Islamic art was a point of influence and a starting point for a modern theory of tiling theory. It started somewhere there. And there were many different problems stated by the scientists. One of the first people who was working on this was Kepler, German mathematician Kepler, but before him there were other attempts. And there was one attempt of finding, there was a few attempts of finding a periodic tiling. I will come back to aperiodic tiling just in a moment, but what you have here, this is the technique that was invented by a postman, not mathematician, okay? Robert Ammann was a postman. He was studying for a moment of mathematics, but he got bored so much with studying at the university, so he dropped it down and he just found his place in a post, and he wrote one day that being a postman is just giving him a lot of time for thinking. So he invented two methods, two things that are quite important for us. I call them deflation rules. So you have a shape like this, a rhombus, and you can divide it into parts like this. And this part is half of the square, and then you have 2, 3, 4 parts of square. You have two identical rhombi like the main one. And also, if you take a square, if you cut it this way, then you create identical rhombi like this one. You can create squares. And if you take, for example, here what I did, okay, I don't remember exactly what I did, okay, but I think I took 4 squares and I was going down, down, down using this technique to create this pattern. It looks like Islamic, and if you see the back, no, okay. Now, I have to go back. If you look at this thing, there is some sharing similarity between this pattern and the pattern of Robert Ammann, based by Robert Ammann rules. Okay, let's go further. This is picture, and many people are talking about this. This is Penrose tiling. Now I can talk more about periodic and aperiodic tiling. You see, when we're making floors, because tiling is related to floors, we usually have a few shapes. And sometimes we have only squares, sometimes we have rectangles, sometimes we have triangles, or sometimes we have hexagons, and we tend to build regular patterns. What means by regular? If you take this pattern, if you move it somewhere farther, you will cover the old pattern without a change, okay? So the pattern will overlap with the old picture exactly the same. Now people started thinking, can it be done in such a way that we have a set of tiles, let's say 2 types of tiles, and it doesn't matter what kind of pattern we build, it will be never periodic. Ammann invented a pattern like this, but here I'm just showing you something that comes from Penrose tiling. Penrose invented a few ways to do aperiodic tiling. One of the ways is showing here. It is using 2 shapes here, okay? I said this is one of the ways. One of the shapes is a dart that looks like this. This is the brown shape. And another shape is like this. This is a kite. Only 2 shapes. And using these 2 shapes, you cannot cover the plane in a regular way. It means whatever you do, you will be not able to take your pattern, translate it to another place, and get exactly the same. So this is the pattern. Now, one of the things when you do Penrose styling is where to start. If you start from a point, because you have to start from somewhere. So you start from a point, and there are really 7 shapes to start around the point. Only 7 shapes. This shape here, which I show here, it is a star. And then you can put shapes around of it in such a way, like here, there's no other way to put the blue shapes or any other shapes around the star. This is the only way. Starting from this point, you can build whatever you use. So this is what people are calling the star empire. Now, why I'm talking about this here? Let's go somewhere else, and we'll come back to this point. This is the Sheikh Zayed Mosque. It is in Abu Dhabi. It is one of the most beautiful mosques I have seen in my whole life. Even from outside, when you look at this, there's such a glory there that you really don't want to leave this place. And Sheikh Zayed Mosque, it is the quite recent building. It has a lot of interesting things. It was built in a mathematical way, using many mathematical principles. But when you are inside, you see a lot of different decorations. And you remember on the beginning, I said I was walking through the Sheikh Zayed Mosque with the lady who was a teacher of mathematics. And we were looking at this pattern, and she said, oh, that's good imagination. And I said, no, that's mathematics. Look at this. This is Penrose styling. And look at this design. Do you see the similarity between this? That's a star here. That's a shape, pentagonal shape is here. Then you have to look at these half stars around, and you have to look at these shapes around here. Okay? Then you're getting the big things like this, and you're getting them here, okay? They are around. So this pattern shares a lot of similarity with the Penrose styling based on the empire of stars, okay? Now, I have to finish. I think my time is over. I have to go back to Istanbul. When you go to Üsküdar, you know where is Üsküdar? Üsküdar is on the other side of the Bosphorus. Very nice place with a number of interesting things. And I found in Üsküdar the Shakirin Mosque. Why I'm talking about this mosque here? Because it's highly mathematical mosque. The whole mosque is more or less half of the sphere. The sphere was cut down, then it was cut from 4 sides, okay? So each cutting of the side, it is cutting of the sphere. And the ceiling of this mosque is part of the sphere. There's even more. If you look at this minbar here, it is circular. I went there 2 days ago. I managed to go just to the end so I can see the profile on this. This is not half, a quarter of a circle, really. So the whole mosque is built based on circle and sphere. This is really mathematics. Now I wonder how many people going to this mosque will see these facts. They will say, okay, that's nice design. Some of them will say, oh, that's funny design. But no one will say, oh, that's mathematics. Thank you.